Have you ever wondered how a computer can look at something as messy as your handwritten notes and actually understand them? Or how a smart flashcard app knows if you've correctly drawn a character? It all comes down to a fundamental question: what does it truly mean for a computer to recognize something, like this handwritten digit 7? How does it go from a jumble of pixels to a confident identification? This question isn't just academic. It's the bedrock of the powerful AI study tools we're exploring in this series. Tools that can read your notes, generate summaries, or even help you practice drawing complex diagrams. In this lesson, we're going to peel back the layers and understand the core mechanism. We'll build, piece by piece, the intuition behind how a computer sees and interprets a simple image, using our handwritten 7 as our guide. First, let's simplify. To a computer, an image isn't a picture, it's just a grid of numbers. Each pixel in our handwritten 7 can be represented by a numerical value, say, from 0 for pure white to 1 for pure black. Imagine our 7 is drawn on a tiny 28 by 28 pixel canvas. That's 784 individual pixels. To process this, the computer takes all these numbers and lines them up, one after another, into a single, long list. We call this an NLT, span style equals color, #0000FF, and GT, input vector and LT/span and GT. Now, why do we do this? Because we need a way to make a decision. Is this list of numbers a 7 or not? The simplest way to make a decision based on many pieces of information is to give each piece a certain importance and then add them all up. This importance is what we call A and LT, span style equals color, #00FF00, and GT, weight and LT/span and GT. Think of it like this: when you look at a 7, certain parts are more crucial than others. The horizontal bar at the top, the diagonal stroke, these are key features. A high-end LT, span style equals color, #00FF00, and GT, weight and LT/span and GT, means that pixel is very important for identifying a 7. A low-end LT, span style equals color, #00FF00, and GT, weight and LT/span and GT, means it's less important, or even detrimental if it's a pixel that usually isn't part of a 7. So, for each pixel's value in our NLT, span style equals color, #0000FF, and GT, input vector and LT/span and GT, we multiply it by its corresponding NLT, span style equals color, #00FF00, and GT, weight and LT/span and GT. This gives us a weighted value for each pixel. After multiplying each pixel value by its NLT, span style equals color, #00FF00, and GT, weight and LT/span and GT, we sum all these weighted values together. This gives us a single number, a kind of raw score, indicating how 7-like the input image is. But why do we need one more piece? Imagine a scenario where even a non-7 image might have some pixels that, by chance, align with some positive NLT, span style equals color, #00FF00, and GT, weights and LT/span and GT, leading to a slightly positive sum. We need a way to adjust our baseline, to make it harder or easier to reach our 7 threshold. This is where the NLT, span style equals color, #FFFF00, and GT, bias and LT/span and GT, comes in. The NLT, span style equals color, #FFFF00, and GT, bias and LT/span and GT, is a single, extra number that we simply add to our weighted sum. It acts like an adjustable offset, shifting the entire sum up or down. So, our calculation now looks like this: we take each and LT, span style equals color, #0000FF, and GT, input pixel and LT/span and GT, multiply it by its and LT, span style equals color, #00FF00, and GT, weight and LT/span and GT, sum all those products, and then add the and LT, span style equals color, #FFFF00, and GT, bias and LT/span and GT. This combined operation is the core of what a single neuron does in a neural network. It takes many inputs, applies and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, adds a and LT, span style equals color, #FFFF00, and GT, bias and LT/span and GT, and produces a single output number. But this raw output number isn't a clear yes or no. It could be 5.3, or -2.1, or 10.7. We need to turn this continuous number into a clear decision. This is the job of an and LT, span style equals color, #FFFF00, and GT, activation function and LT/span and GT. For simplicity, let's imagine a very basic and LT, span style equals color, #FFFF00, and GT, activation function and LT/span and GT. If the number is above a certain threshold, say 0.5, it outputs a 1, meaning yes, it's a 7. Otherwise, it outputs a 0, meaning no, it's not a 7. So, for our 7, if the weighted sum plus bias is high enough, this neuron will activate and confidently say 1, meaning I think this is a 7. But we don't just want to know if it's a 7. We want to know if it's a 0, or a 1, or a 2, all the way up to 9. So, instead of just one neuron, we need 10 of them. Each of these 10 neurons has its own unique set of and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, and its own and LT, span style equals color, #FFFF00, and GT, bias and LT/span and GT. The 7 neuron will have and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, tuned to recognize a 7, while the 0 neuron will have and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, tuned for a 0, and so on. When we feed our handwritten 7 into this system, the 7 neuron should ideally output a high value, while all the other neurons should output low values. This entire structure, the and LT, span style equals color, #0000FF, and GT, input layer and LT/span and GT, the connections with their and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, and LT, span style equals color, #FFFF00, and GT, biases and LT/span and GT, and the and LT, span style equals color, #FF0000, and GT, output layer and LT/span and GT, of neurons, is the simplest form of a neural network. Now, imagine doing this by hand. For our 28 by 28 pixel image, that's 784 pixels. Each of those pixels needs a and LT, span style equals color, #00FF00, and GT, weight and LT/span and GT, for each of the 10 output neurons. That's 7840 and LT, span style equals color, #00FF00, and GT, weights and LT/span and GT, plus 10 and LT, span style equals color, #FFFF00, and GT, biases and LT/span and GT. This is how a computer recognizes our handwritten 7. It's not magic, it's a systematic process of breaking down the image into numbers, applying learned importance values. The AND-LT, span style equals color, #00FF00, and GT, weights and LT slash span and GT, and LT, span style equals color, #FFFF00, and GT, biases and LT slash span and GT, and then making a decision based on the combined evidence. This fundamental understanding of how a neural network processes information is what underpins many of the smart features in AI-powered study tools, from optical character recognition to intelligent content recommendations. So, what did we learn today?